Hello and welcome back. So last time we saw how to construct a SR flip-flop, the set reset flip-flop with NOR gates. This time we're going to go over a problem with an SR flip-flop constructed with NAND gates. It has slightly different behavior. I would suggest you look out for those. And also notice that there's an initial state given in the prompt. This is because we're analyzing a sequential circuit where previous outputs matter. So I would recommend you pause the video right now and get some time to think about this, try to figure it out, and come back when you're finished. All right, hopefully you paused the video and had some time to think about this. Now let's go over this together. So the S bit is set to 1, R bit is 0, Q is 0, Q prime is 1. So now we change the R bit to 1. So this input becomes 1. We don't know what the other input is. Well, we do know because it's this 0 right here because it travels here, right? So it's 0 right here. 1 and 0 is 1, right? So we get 1 here and we feed this 1 back here. This is 1 right here. Sorry, I shifted a little bit. And this is still 0. So it looks like the circuit stabilizes and Q is 0 and Q prime is 1. Now we're changing S to 0 now. So this input becomes 0, this output becomes 1, this output at the same time becomes 1, this 1 gets feeded down here, and this becomes 0, which means this becomes 0, this 0 then feeds back up here, 0. It doesn't change, the output is still 1. Right, it's still 1, and it looks like it stabilizes there. So the output is 1, 0. Now we change S back to 1. So this becomes 1 again. 1 and 0 is still 1, right? 1 gets passed down over here. It doesn't change. And the output down here doesn't change either. So the overall circuit remains the same and stabilizes at that point. So it's still 1, 0. Now we change both of them to 0. So let's do it one by one. So let's change R back to 0 first. This becomes 0, this becomes 1, this becomes 1, and then this gets feeded up here. This becomes 1. And this becomes 0, this becomes 0, this becomes 0, it's still 1, doesn't change anything. 1 gets feeded back, doesn't change anything, and stabilizes at 0, 1. Now we change S to 0. I'm sorry, it's very messy, and that kind of happens when you analyze sequential circuits this way, so bear with me. So S sets to 0, this becomes 0, this becomes a 1. And this 1 gets feeded down, this becomes a 1. It doesn't really change anything, it's still a 1. Remember that it became a 1 right here. Okay, 1 gets feeded back up, nothing changes, and it stabilizes at 1, 1. And this kind of answers the next question as well. We can't have S and R equal to 0 because we know that Q and Q prime must be opposites of each other. And in this case, we clearly see that they're not opposites of each other. And that would be the explanation you give. Note here is that if you think about it, it's kind of doing the exact opposite thing as the SR flip-flop we saw before constructed with the NOR gate. As we talked about functional completeness before, we can literally construct a NOR gate with NAND gates. I would recommend you take some time to see how you can construct the behavior we got before with the SR flip-flop with NOR gates with only NAND gates. That's it for this video and for SR flip-flops in general. Next time we'll talk about JK flip-flops, which is a different kind of flip-flops. See you later.